thanks for stopping in. I was just thinking about you, actually. I was thinking about how we need to start talking about probability distributions. Now, I know I've been doing a lot of probability lately, but it leads into some important statistics that we're doing this unit that starts with probability distributions. Actually, I have a set of dice here. Well, more than a set of dice. I have 4 dice. So let's play a little game with my 4 dice. Imagine I'm trying to roll as many 6s as possible. I got 1 6. Let's try again. 1 6 again. No 6s. This might be an example of a probability distribution. What are the possible outcomes of trying to roll 6s with 4 dice? One possibility is that I get no 6s. Another possibility is that I get 1 6. There's 1 6 there. So I could have no 6s, 1 6. I could have 2 6s, 3 6s, or 4 6s. Those are all the possible outcomes. And we could actually figure out the probability of each of those things happening. The probability of no 6s, 1 6, 2 6s, all the way to 4 6s. And that would be called a probability distribution because it takes into account all of the possible outcomes. Come on, let's take a look. So looking at the example with 4 dice and trying to get as many 6s as possible. Of course, the probability of getting a 6 is 1 out of 6, and the probability of not rolling a 6 is 5 out of 6. So the probability of rolling no 6s, well, 5 out of 6 times you're not going to roll a 6 on the first die. And then just think about each die being another event. 5 6s times 5 6s 4 times, or 5 6s to the power of 4, is the probability that every single dice turns up with a number other than 6. And that works out to approximately 0.48225. Okay, how about the probability of rolling exactly 1 6? So imagine it like this. Imagine the first roll is a 6. And the next 3 rolls cannot be 6s because we want exactly 1 6. So that would be 5 over 6 to the power of 3. Now that's only one way to roll exactly 1 6. It doesn't have to be the first die. It could be the second die, the third die, or the fourth die. So we actually multiply by 4, or sometimes we might say 4 choose 1. Choose one of the dice to be the 6, and the rest are not. And that works out to approximately 0.3858. Notice this probability question is the special probability problem we've already talked about, similar to the Lego problem or the problem where we tried to decide different probabilities for guessing on a multiple choice quiz. All the same idea. Probability of rolling 2 6s. Think about the 2 6s being the first 2 rolls and the non-6s being the last 2. But then there are 4 choose 2 ways to determine which of the rolls happen to be the 6s. That probability works out to about 0.11574. 3 6s. So now we're at 4 choose 3. Hopefully you're starting to see the pattern here. Times 1 over 6 cubed times 5 over 6. Again, kind of pretending that the first 3 rolls were 6s and the last one was not a 6, but then multiply that times 4 choose 3 because there are 4 choose 3 ways to pick the 3 rolls that might have been a 6. And that works out to about 1.5%, or 0.01543. And then finally, exactly 4 6s is an easier one to calculate. That's just 1 over 6 to the power of 4, which is a very small number. It's possible, but not very likely. Now the pattern does continue. If you wanted to for this one, you could actually say 1 over 6 to the power of 4 times 5 over 6 to the power of 0, since 5 over 6 to the power of 0 is 1, and then multiply that by 4 choose 4, which is also 1, but it's not necessary to write that stuff in. So here are our probabilities, and you can see that the no 6s has the highest probability, but rolling 1 6 is still very reasonable at almost 40%, and 2 6s is over 11%, so that's also within the realm of possible. And it starts to get pretty low when we look at 3 6s or 4 6s. This is going to be our example of what's called a discrete random variable. That's a variable that assumes a unique value for each outcome. So we could call the number of sixes rolled, we could refer to that as a discrete random variable. And it can take on 5 values, 0, 1, 2, 3, or 4. Remember the word discrete means like countable or whole numbers. So it can't take on 1.5 or 2.2. You can't roll 2.2 sixes. You can roll 0, 1, 2, 3, or 4. And we often assign discrete random variables a capital letter, and X is very common. So we could refer to X as being the number of sixes rolled when rolling 4 dice. Okay, and then X can be 0, 1, 2, 3, or 4. Discrete random variables are used for probability distributions. So a probability distribution is a function that provides the probability of X taking on each possible value. That's all it is. So here is a probability distribution. All I did was take those values from the other slide screen and write them out. So this notation means the probability of X being 0. So the probability of the number of sixes rolled being 0. The probability of X equaling 1. The probability that the discrete random variable X, the number of sixes rolled, the probability that that's equal to 1 is 0.3858. So one way to talk about a probability is just list the values. Since X is a discrete random variable, you're going to be able to list them because they're countable. They're not infinite in size. There's no such thing as 1.1 or 1.5 or anything like that. You might summarize them in a table like this. Okay? X and P of X. Or you might actually come up with a graph, kind of like a histogram, where here I've got the number of sixes rolled and the probabilities, and I've graphed them. Notice they start very high at 0 and then drop off. You can't even see the probability of getting 4 sixes. It's so small. So I have a question for you, and that's not on your handout, but what would I get if I took all of these values and I added them up? What should they equal? Now, they're not exact values. We could have done exact values. We'd have large, like fractions with very large numbers in them possibly, but we could have done it. I chose to round them. But even still, hopefully you realize those should sum to 1. And the reason they should sum to 1 is those are all the possible cases. When you roll 4 dice, you either get 0 sixes, 1 6, 2 6, 3 sixes, or 4 sixes. If those are all the possibilities, then 100% of the time, one of these 5 things is going to happen, in which case the probability is 1 or 100%. Let's think about actually doing this game. Suppose you roll your 4 dice the same way I did, and you get no sixes. Is that lucky or unlucky? Is that typical? In some ways, you might argue it's fairly typical because the probability of getting no sixes is the highest probability of all 5 outcomes. However, it's not over 50%. So over 50% of the time, you would expect to get 1, 2, 3, or 4 sixes. So in some ways, we might argue that if you rolled no sixes, you did, worse than average if your goal is to roll sixes. And that gets into the idea of expected values. What is kind of the average amount of sixes you should get when you roll 4 dice? So expected values, all discrete random variables have expected values. So like I said, the highest probability is you get no sixes, but that's different than what you would expect to get, which is more of an average. It's kind of like if millions of people played this game, rolled 4 die, and counted the number of sixes, we could calculate the average number of sixes each person has, and that would not be 0, and it would not actually be 1. Formally, an expected value for a discrete random variable is given by this formula. Calm down. I know that looks super confusing. It's not too bad. We've got an expected value for a random variable x is equal to, this just means sum. It's the sum of all the probabilities times the value of that probability. And it's going to really make a lot of sense if you see an example, like we used the example here. So here we had 5 different possibilities, each associated with a probability and an outcome. So all we do to do this example is, what's the probability that you get that x is equal to, so we start with I equals, sorry, that should say I equals 0, not I equals I equals 0 to n. What is the probability that we get so we think about like x1, x2, xn being all the possible values x could take on. So in our example of the die, this was a possibility all the way to this. So we're going to sum all of those probabilities, and then we're going to multiply them by the number of sixes in this case. So 0, 4, and so on. So starting with 0 as an outcome, 0 sixes, that had a probability of 0.482253, plus the probability of getting 1 6 times 1. Probability of getting 1 6 is 0.385802, plus the probability of getting 2 6s times 2. Probability of 2 6s, plus the probability of 3 6s times 3, plus the probability of 4 6s times 4, which is a very small number. Now, if you were to go ahead and add all of those up, okay, multiply by 0, by 1, and so on, and do it, you would find you get a number very, very close to 0.66666 continued. In fact, if you used exact values instead of these decimals, you would get 2/3 exactly. Think about what we're doing here. Imagine this game being played over and over and over again. Like 38% of people would get 1 6, 48% would get 0 6s, 11.5% would get 2 6s. So if we take 11.5% of 2, it's like we're talking about calculating the average number of sixes. And in here, the expected number of sixes, or the average number of sixes people would get, would be 2/3. Notice that this isn't surprising at all. We could have actually just said, look, the probability of getting a 6 is 1 out of 6. So in your 4 rolls, 1/6 of those you would expect to be 6s. 1 6 times 4 is 4 6s, which is 2/3. So expected values can often be very simple to calculate. This definition is important, and I'll show you an example where you can't just do something simple like this, but that's all you're doing here. Let's consider another probability distribution and another expected value. Consider X being the number of female babies in a family planning to have 2 children. Let's assume that there's a 50% chance your baby is a female and a 50% chance your baby is born a male. Okay, so if you're having 2 children, you might have 0 female babies, 1 female, or 2 females. What's the probability of not having any females? Well, that means the first child is a male and the second child is a male. Well, half times a half is the probability of that is 1/4. Let's look at 2 females. The probability of 2 females is also 1/4. Half the time the first child will be a female times half the time the second child will be a female. 1/4. Now, how do I calculate the probability that exactly 1 female? Well, I could look at it and I could say, look, 1/4 plus 1/4 is a half. So a half of the time, like I know this has to add up to 1. Or you could say, well, you know, the probability of having a male and a female is a half times a half. Or add that to the probability you have a female and a male is also a half times a half, which is 1/4 plus 1/4, which is also a half. So there's lots of ways to get that. Okay, so that's our probability distribution. That's exactly what a probability distribution is. X is the number of female babies. The possibilities are 0, 1, 2, and then I've written their associated probabilities beside them. For the expected value of X, we take 0 times it by 1/4, plus 1 times it by a half, plus 2 times it by 1/4. And what do we get? Well, 0 times 1/4 is just 0, plus a half. 2 times 1/4 is 2/4, or also a half, and a half plus a half is equal to 1. There's our expected value. Is that a shock? I would hope not. I would like to think that if you're planning to have 2 children, on average, you'd expect one of them to be female. For our last example in this lesson, let's look at a hockey game raffle tickets. Sometimes you go to a local hockey game and they might sell 50-50 tickets or something like that. So in this example, ticket costs $5 and 2,000 tickets are sold. They then put the tickets in some sort of container and draw them at random. And you might win the grand prize. There's 1 grand prize. There's 2 runner-up prizes of $200 and 5 $50 prizes. So they draw in total 8 prizes. We could talk about X being a random discrete variable where X is the prize money you win. X can take on some different values here. It could take on 1,500. That's a possibility. You might win the grand prize. It could also take on a value of $200 or a value of $50. And finally, it could also take on a value of 0. We should include that as well, because a probability distribution does need to include all the possible outcomes. So we can now calculate the probability of each of these things happening. There's a 1 out of 2,000. That's your chance of winning the grand prize. Only 1 ticket is drawn. There are 2 runner-up prizes out of 2,000 tickets. So 2 out of 2,000 is the probability you win that, which does reduce to 1 in 1,000. The $50 tickets, there are 5 of those. So 5 out of 2,000 is the probability you win the $50. That reduces to 1 in 400. And finally, for 0, there are 8 prizes. So there are 1,992 tickets that win nothing. And that's your probability of winning nothing. It actually reduces to 249 out of 250. And there we go. That's a probability distribution. It's exactly what it is. Well, if we have a probability distribution, we can always calculate an expected value. Now, this expected value, this is the first one that's not obvious how to calculate it. So you do need to use the formula. So we take the probability of each outcome happening, multiplying by the value of that outcome. So, for example, $1,500. Multiply that by its probability of 1 out of 2,000. Plus the probability we win the $200 prize times 200. So 200 times 1 in 1,000. Plus our probability of winning $50, which is 1 out of 400. Plus our probability of winning $0. And this is the expected winnings. Notice this one's just 0, okay? Because you don't win anything there, so it doesn't matter what the probability is even. So we get 1,500 over 2,000 plus 200 over 1,000. Sorry, 200 over 1,000 plus 50 over 400. If we add those up, it's actually easier to add them if they're all out of 2,000. Making a common denominator, 400 over 2,000 plus 5 over 2,000. Okay, and that gives us, sorry, that should be a plus sign there. That gives us 1,905 over 2,000. Now we could reduce that, or really we could just turn it into a decimal. And we'll talk about why a decimal is probably okay here. You get 0.9525. Since X is our winnings, okay, the prize money one, the expected value, E of X, is also prize money one. This is in dollars. That's the expected winnings on your $5 ticket. So in a way, that's kind of like talking about the value of your ticket. Your ticket's worth about 95 cents, your $5 ticket. That's the average winnings for each ticket. In total, each ticket is, a little over 95 cents. Okay, that's it for this lesson. Good luck with the work, and bye until next time.